Good morning, children. Today we are continuing with general organic chemistry. This is the second lecture on that. In the last session we have discussed about inductive effect, and today we are continuing with the other effects which can be included to discuss the various properties of the compounds. The first effect which we are discussing today is electromeric effect. Now let's understand what exactly this is. This is defined as the complete transfer of the electrons. So basically what is there in it? It involves complete transfer of the electrons of multiple bond. We know that multiple bond is made up of sigma and pi. Sigma and pi electrons, that is sigma and pi bonds are there in it. So it involves the transfer of multiple bond, that is electrons which are there of the multiple bond to one of the bonded atom. Means if the bond is there between two atoms, the pi electron will move towards one of the atom. Which atom it will move? On that basis it is further classified into two categories. And when it is going to move, it will move only in the presence of the attacking reagent. So there are two things happening. Number one, the electrons, the pi electrons are moving. Number two, the attacking reagent, when it comes, the pi electron will move. Right? Now, it is a temporary effect because it is visible only in the presence of the attacking reagent. Okay? It is only observed in the presence of the attacking reagent. So, we say that it is a temporary effect. For inductive effect, we said that is a permanent effect. Okay? This is temporary effect, only visible in the presence of the attacking reagent. Now, it is of two types. Positive electromeric effect and negative electromeric effect. Positive electromeric effect is defined as when the electrons of the pi bond are transferred to that atom of the double bond to which the reagent gets finally attached. I don't know whether with just a definition we may not be able to understand. We'll take example for better understanding. Suppose you consider alkene. There is a double bond between two carbon atoms. And the reaction is in the presence of H+, that is acid medium. So H+ is positively charged. Positively charged means it is electron loving. So we can say electrophile will start this reaction. So when the electrophile approaches this alkene is having one sigma and one pi bond, and we know that pi bond is weaker bond. So the pi electrons will start moving towards one of the atom. When they move towards one of the atom, suppose they move towards this particular atom, because both the carbon atoms are having a same type of the bond, that means it is a symmetrical alkene. So this H+, that is electrophile, so if these pi electrons are coming this side, the electrophile obviously, because it is in need of the electrons, it will also attack the same atom. That means the pi electrons and the electrophile both attack the same atom. This is positive electromeric effect. Now you just read the definition once again, see if it is clear. If the pi electrons of the bond are transferred to that atom of the double bond to which the reagent gets finally attached. That means the reagent and the pi electrons both attack the same atom. It is positive electromeric effect. Got it? Now, negative electromeric effect. Negative electromeric effect means when the pi electrons and the attacking reagent, they attack the different atoms which are having a double bond. Let's take example of C double bond O, carbonyl compound. We are taking the example. So suppose this is attacked by say Cn minus. Cn minus is negatively charged species. It is in need of the positive. So we can say it is a nucleophile. So until and unless the nucleophile approaches, it cannot undergo this effect. So that is why we are saying it is only in the presence of the attacking reagent. So now what will happen is this pi electron, there is a double bond between C and O. So this pi electron will be more drifted towards O. In this case, it can be either side. But here, because O is more electronegative, obviously the pi electrons will be more drifted towards O. So when they are going towards this side, this O will develop a negative charge, partial negative charge, and this carbon will develop a positive charge. This is positive seeking reagent. So what will happen? The Cn minus will attack this carbon atom because it's a nucleophile. It will attack carbon atom. So what is happening? Electrons of the pi bond of this double bond, they are moving this side towards O, and the nucleophile is going to the other atom. So the two are attacking the different atoms. So it is said to be negative electromeric effect. The effect is clear. It's a temporary effect visible only in the presence of the attacking reagent. Now we'll talk about another effect, that is resonance effect. Now what is resonance effect? Resonance effect, first let me tell you this. It is also called as mesomeric effect. It is also called mesomeric effect, and the basic requirement for a compound to exhibit mesomeric effect or the resonance effect is either there should be two pi bonds, lone pair or pi bond, or we can say two pi bonds, pi bond and pi bond, or lone pair and pi bond if they are in conjugation. If they are in conjugation, then this effect is visible. Lone pair and pi bond, or pi bond and pi bond. So two pi bonds if they are in conjugation. Conjugation means alternate. If they are present alternate to each other, then this effect will be visible. So this effect will be able to explain many properties. Okay, now let's take examples of two types. Even this is plus and minus R effect, plus or minus M also we can say. So I'm taking example of plus R effect, right? Positive resonance effect, or plus M effect also we can say. So CH2 double bond CH and Cl, right? So on this chlorine there are three lone pairs of electron, three lone pairs, right? So these three lone pairs and this pi bond are in conjugation. Conjugation means you alternate. There is a pi bond, then there is a single bond, and then lone pair. So lone pair, single bond, pi bond, they are in conjugation. So this effect will be visible. Okay, now when this is having many lone pairs, so this will donate its electron pairs this side. It will start moving this side, and then this, when it comes here, the valency will be disturbed. There will be a double bond here. So when double bond is there, this carbon will have 5 bonds, which is not possible. So this pi bond will shift further. So this will result into the formation of CH2 single bond CH, now a double bond Cl, and now one pair has migrated. So only two pairs are left over now, because this carbon has this chlorine has lost electrons. So there will be a positive charge here. This has gone here. So this will develop a negative charge, plus one lone pair extra will be shown on this particular carbon atom. So this type of effect in which the groups donate the electron towards the double bond. There is a double bond here. So it is donating electron pairs towards the double bond. They are moving towards the double bond or towards the conjugated system. We will take the example of the conjugated, aromatic system. That also I will take the example. So they are said to be positive resonant effect showing groups. Let me take example of phenol. I'll draw the example structure. This is phenol, right? O, and there is H. There are two lone pairs on this oxygen. Okay, so now what do you observe? In this, two lone pairs and pi bond are in conjugation. They are alternate to each other. So what will happen? This will start migrating. So this one of the lone pair will start moving this side. It will go towards the bond between carbon and oxygen. When this goes here, one of the pi bond will shift further. So the other one structure, what changes you made in the first structure, now we will show in the second structure. So this is as such, nothing has happened to it. This is now a double bond. This is a single bond. Now O, one lone pair only left because one has gone, and this will acquire a positive charge. This has come here, so you will get one negative charge, or you can say one lone pair will be shown here. And these two structures, whatever structures are there, they'll be shown by, both side arrows. Why? Because you cannot say this is existing or this is existing. All are equally existing. So they are said to be the different resonating structures. Let's take another example now, because whatever has happened here, in the first step we have shown here. Now again this will go, and this pi bond, always it is happening like that. Lone pair is pushing, pi bond is going further. Lone pair is pushing, pi bond will go further. So what changes I made in the second structure, I'm going to show in the next one. Because this has come here, it will be a double bond. This has come here, means there will be a negative charge of the lone pair. And remaining, nothing has happened to the, structure. There is positive charge over here. Again, this lone pair will push as if, and the pi bond will go further. And what changes we made in the third structure, now I'm going to show in the fourth structure. This is as such. This is a double bond. There is a negative charge. You can just compare with the previous structure which is drawn over here. So one lone pair here, positive. Now again, this will go here, and this pi electron will go back to original place from where it started. So this is coming here, this is here, double bond. No, sorry, the double bond has gone. This is now a single bond. Sorry, this is now a single bond, right? Now O, H, and both the lone pairs back on O. Now how do you remember exactly these? You can just, frame some sort of animation in your mind. This is coming from behind, this is going further, again it is pushing, going further, this is pushing, going further, and so on. Now one very interesting thing in this, you observe the resonating structure. This is structure of what, children? Phenol. With respect to this OH, you found the negative charge is coming at ortho position or at para position. This is again another ortho position. So what are you observing? In the different resonating structures, the negative charge is coming either at ortho or para with respect to OH. That means we can say phenol will undergo electrophilic substitution reactions at ortho and para position. It's a reason question which can be asked. The statement can be, phenol undergoes electrophilic substitution reactions at ortho and para position. Justify. How are you going to justify? You will draw the resonating structures and you will see that the negative charge is coming at ortho and para position. So that means the negative charge is coming there, means obviously electrophile, electron loving species will come and attack here at ortho and para position. Clear? One more example of positive resonance effect I am going to show. I am taking the example of chlorobenzene. Okay, this one. Lone pair pi bond in conjugation, alternate to each other. So this lone pair will start migrating. So this is coming here. The next, what changes I made in the first structure I am going to show here. This is negative. When two lone pairs have, two electrons have come here. There is a double bond here, chlorine, and out of three pairs only two are left over. This chlorine will develop a positive charge now. This will be like this. Again, this will go here. This lone pair will push, pi bond will go further. Always the lone pair is pushing and the pi bond goes further. So there is a positive double bond here. Two lone pairs as such, positive charge over here. This is the double bond. See what changes were there? I am just showing here, nothing great in it. This will go here, again it will go here, and the next structure comes out to be, this is double bond, this is a negative charge, of course that lone pair, double bond, Cl, positive charge, and two lone pairs back on chlorine. Clear? Now what changes we have shown here? This will go here, again it will go back. Means it's somewhat similar. One structure you followed, the others you will be able to draw very easily on your own. Double bond, This is a double bond. Single bond now. Chlorine, again it gets all this. See, this has gone here, means all three back. So what you find, the first and the last structure are, as if object mirror images. The pi bond positions are like this. And again you can see here the negative charge with respect to chlorine is coming at ortho and para position. So we can also say chlorobenzene undergoes electrophilic substitution reaction at ortho and para position. Justify. So you can justify by drawing the structures and seeing the negative charge where it is coming. Another interesting thing. In all the structures you are observing, the center ones, there is a double bond between carbon and chlorine. Carbon and chlorine. Carbon and chlorine. Double bond. So, what we can say is, this is haloarine, chlorobenzene. This bond, carbon-chlorine bond, in this chlorobenzene, this bond cannot break easily. They cannot break easily. Okay, so there is a question asked, that means it is basically what? ARX, this is read as aryl group. To this halogen is attached. Aryl group cannot break up and form Ar plus and X minus. That means if it is forming a positive charge species, why it cannot form actually? I told you there is a double bond between them. Due to the partial double bond character, this bond cannot break. So there is a question, actually a part of class 12. It is asked that aryl halides cannot undergo nucleophilic substitution reaction. NSR. Aryl halides cannot undergo nucleophilic substitution reactions easily. Nucleophilic means they should be attacked by a nucleophile. To be attacked by a nucleophile, the bond should break and it should form Ar plus. Because it cannot form Ar plus, because the bond cannot break, it cannot undergo nucleophilic substitution reaction. Right? Even here, children, one reason question can be asked. Like, this is alkene example I had taken. The question can be alkenes. This is alkene. Alkenes undergo electrophilic addition reactions. Why? Why do they undergo electrophilic addition reaction? Because when something is coming here, the double bond is breaking. So obviously addition, it is forming a single bond. Yes. So it is formed, that is unsaturated compound is changing to saturated. So it is undergoing addition. And electrophilic addition, electrophile is attacking it. Because, why do they undergo electrophilic addition? You will say, because the double bond is between two similar atoms. Two similar atoms means electrons will be equally distributed. So any attacking reagent, that is electrophile, can come and get attached to it. Whereas for carbonyl, this is CO group. CO means carbonyl group. We can say carbonyl compounds undergo nucleophilic addition reactions. Why? What is the question? Carbonyl compounds undergo nucleophilic addition reaction. Why do they undergo nucleophilic addition reaction? Because there is a difference in the electronegativity between carbon and oxygen. The pi electron is more drifted towards O. Carbon gets a positive charge. Carbon gets a positive, will be attacked by a nucleophile. So they can undergo nucleophilic addition reactions. Now, minus R effect we will take. Now, what is minus R effect? Those groups which withdraw the electrons of the double bond towards themselves. They are said to be exhibiting minus R effect. So, I'll draw one structure and explain it to you. Suppose I am taking benzaldehyde structure. This is benzaldehyde, C6H5CHO. Pi bond conjugation, they alternate to each other. This being more electronegative will pull electrons toward itself. When this goes here, this carbon gets positive comparatively. So it will try pulling this bond towards itself now. So what changes I made in the first structure, I am going to show here. This will be positive, double bond. This is O, single bond now, a negative. Now when this has gone here, means this will be a positive thing. Right? Now in this, the ring will have a positive. So now only one arrow will be shown, because to satisfy this plus charge, pi bond will shift. And when it shifts here, in the next structure, what you have is, this is a double bond, this is a double bond as such. Nothing has happened to this now, H, and there will be a positive charge developed here. So now because this is positive, this will go. And keep in mind, always electrons move and the arrows will be only in one direction. They are moving in this direction. So they will move in this direction only, anti-clockwise. If they are moving in clockwise, they'll move in clockwise only. That depends what example we are considering. So what changes I made in this structure, I'm going to show in the next structure. There is a double bond, a positive charge over here, double bond, CO, negative, and H. To satisfy this positive, again this bond will shift. When this goes here, again this negative will come back. So basically, what is resonance? It is just movement of the electrons from one to the another one, right? So now what changes I made in the first structure, this fourth structure I'm going to show here, and you get this structure, that is the last structure. Clear? Now, one structure I'm just telling you to draw on your own.